Nyana neko, nyana no nyana neko, nyana neko. Nyana 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 neko, neko neko, neko neko, neko, neko neko neko. Neck 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 neko neko neck 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 neko. Neko neko neck and the neck go neck 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 neko neko neck 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 neko neko neck neck neko neko. Neko 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 neck 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 neko 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 neck 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 neko 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 neck 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 neko 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 neko. Neko neko neck 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 neko neck 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 neko 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 neko. Neko 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 neck 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 neko neko neck 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 neko 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 neck 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 neko neko neck 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 neko 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 neck neck neko 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 neko.
Oh, Billy.
Neko 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 neck 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 neko neko neck 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 neko neko neck neko.
I almost want to make a clip.
Neko 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 neck 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 neko neko neck 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 neko 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 neko.
I almost want to make a clip. I'm gonna
neko neko
end your clip. I don't know how good it will do though.
Neko.
Ow.
Quit
Quit hitting myself. Quit hitting myself.
Neko 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 neck 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 neko neko neck 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 go neck go neck 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 neko 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 neko.
Oh, Billy.
Neko neko neck 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 neko neko neck 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 neko 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 neko. Neko 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 neko
Oh, Billy. Do I got everything set up? Oh,
neko neko.
one thing I gotta do. I gotta set the music up. We'll put on Skyrim, motherfuckers. And then
Yeah, the neck go, the neck go, neck. Yeah, the neck go, the neck no neck. Yeah, the neck go, yeah, the neck go.
I think I'm ready.
Yeah, the neck go, neck neko, neko neko, neko, neko neko.
I think I'm ready.
Neck 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 neko neko neck neck.
All right. So, like, here's the bad thing. The bad news is that I don't have like any. I don't have like a. I don't have like a Python development set up. I like sort of do. Okay. We'll see what they do. Let's see what they ask me to do. So dismiss this. All right. Oh, what is this? HuggingFace course. How long is this? Okay, let's watch this video. This course will teach you about large language models, LLMs, and natural language process, NLP, using libraries from the HuggingFace ecosystem, transformers, dataset, tokenizers, and accelerate, as well as the HuggingFace hub. Also cover libraries outside of the HuggingFace ecosystem. These are amazing contributions. Let me make this bigger. To the AI community and incredible useful tools. It's completely free and without ads. Understanding LPM and LLMs. While this course was originally focused on NLP, natural language processing, it has evolved to emphasize large language models, which represent the latest advancement in the field, which will probably be going away here soon. NLP, natural language processing, is a broader field focused on enabling computers to understand, interpret, and generate human language. NLP encompasses many techniques and tasks such as sentiment analysis, named entity recognition, and machine translation. LLMs, large language models, are a powerful subset of NLP models characterized by their massive size, extensive training data, and ability to perform a large range of language tasks with minimal tasks, blah, 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 blah. Throughout the course, you'll learn about what exactly was a brief overview. I just found Cat Mike from Deltanu. Oh my OMG, what? Chapters, okay, introduction, transformer models, using transformers, fine-tuning pre-trained models, sharing models, and tokenizers. Deltarune. Diving in the data sets library, the tokenizers library, main NLP tasks, and how to ask for help. Advanced building and sharing demos. Transformers can hear. Oh, transformers can see. Optimizing for production. Chapters 1 through 4 provide an introduction. Holy shit. Chapters 5 through 8 teach basics. Chapters 9 go through NLP. Blah, blah, blah. Requires good knowledge. What? I have zero knowledge of Python. Is better taken after an introduction to deep learning course. Fast AIs. So, my background does not expect prior PyTorch TensorFlow knowledge, though some familiarity of those will help. So I have like no Python background. Ha! But I do have, I have like a good amount of knowledge of deep learning. After you completed this course, we recommend checking out Deep Learning AI Natural Language Processing Specialization, which covers a wide range of blah, blah, blah. Who are we, the authors? No one cares about you all. Oh, what? I'm just kidding. Holy shit, dude. How big is this? Is this the introduction? What's going on here? What is this? Is that a picture? Anyways, let's press play. Hello.
Welcome to the HuggingFace course. This course has been designed to teach you all about the HuggingFace ecosystem, how to use the dataset on Model Hub, as well as all our open source libraries. Here is the table of contents. As you can see, it's divided in 3 sections, which become progressively more advanced. At this stage, the first 2 sections have been released. The first will teach you the basics of how to use a transformer model, fine-tune it on your own dataset, and share the result with the community. The second will dive deeper into our libraries and teach you how to tackle any NLP task. We're actively working on the last one and hope to have it ready for you for the spring of 2022. The first chapter requires no technical knowledge and is a good...
Yeah, I make VTuber clips. Ayo! Like, who's this motherfucker that came up on my recommendation? So I want to build like an LLM. I actually want, since I live stream also, I kind of want to have like something like Neurosama. And I want to have, something that can shoot the shit with me. Chat to people and stuff while I'm doing like stupid things. But like I set up a GPU server. I think you can see me. I have like me building it. Let me go to my channel. My channel live. There's like, I think I was building it here. I like go on. This thing was such a pain in the ass to build because it's like this motherboard's absolutely fucking huge. Into my existence. This is like the biggest motherboard I've ever fucking used in my life. Quite an undertaking, yes, it is quite the undertaking. Yeah. Yeah. So, but like I do have knowledge in this shit a little bit. So This is an old, hello, thanks for the follow. Oh, did I? Ooh. So yeah, I built this. I was like, I was doing AMD. I didn't do NVIDIA. First of all, I don't really like NVIDIA. I don't like their practices lately. So I'm trying to do AMD, but I'm noticing already the drawbacks because everybody builds stuff using NVIDIA libraries and all that. And yeah, so AMD's kind of left in the dust. This is my it's my cave. I like robotics too. So that's why you see like wires and shit there. Get tape, screwdrivers, bolts. There's my camera. There's my microphone for the day. It does. I'm gonna see if I can like undervolt them. The reason why I picked 49060 XTs, 16 gigabytes, and I'm gonna see if I can parallelize that shit. At least like do some jobs with it. This thing is an X9 motherboard, so it still uses DDR3. But here it is. I can log into it. So, yeah, AMD SMI. There's that. Oop. I don't like Ubuntu's like. I need to reinstall a new OS on this shit. Yeah, so I got 4 of them. So I'm gonna see if I can like. I'm gonna use like the guide that they got here for building LLM. So like my background was like in computer vision. And it was just before like the big LLM like breakout. So in the Transformers, like I think I saw the papers, attention is all you need, but I never read it. Yeah. But those turned out to be pretty damn powerful. For my thesis, yeah, TensorFlow is like really cool to like go in and like see how to make algorithms. So like I did that a lot using TensorFlow, but I never like had hands-on with TensorFlow.
Good introduction to learn what Transformers model can do and how they could be of use to you or your company. The next chapters require a good knowledge of Python and some basic knowledge of machine learning and deep learning.
Should I slow
If
this
you don't know
down?
what a training and validation set are, or what gradient descent means, you should look at an introductory course
Gradient
such
descent?
as the ones published by deeplearning.ai
Gradient descent.
or fast.ai.
Sorry.
It's also best if you have some basics in one deep learning framework, PyTorch or TensorFlow. Each part of the material introduced in this course
So
has a
I made
version
my
in
own
both those
framework.
frameworks.
I made my own framework. That was my downfall. I made my own framework.
So you'll be able to pick the one you are most comfortable with. This is the team that developed this course. I'll now let each of the speakers introduce themselves briefly.
Hi, my name is Matthew and I'm a machine.
All right, so as like a clipper who uses editing machines, this audio is fucking terrible. I don't know, is it loud for you all? Like, it's barely like loud for me.
Machine learning engineer at HuggingFace. I work on the open source team and I'm responsible for maintaining particularly the TensorFlow code there. Previously, I was a machine learning engineer at Parsley, who have recently been acquired by Automatic, and I was a postdoctoral researcher before that at Trinity College Dublin in Ireland, working on computational genetics and retinal disease.
Hi, I'm Lysander. I'm a machine learning engineer at HuggingFace, and I'm specifically
He's got that. Is that a scar, or does he have like a...
part of the open source team.
Is that cut
I've
in
been
the-
at HuggingFace for a few years now, and alongside my team members, I've been working on most of the tools that you'll get to see in this course.
They keep on
Hi,
trying to manage things.
I'm Sylvain. I'm a research engineer at HuggingFace and one of the main maintainers
Yeah.
of the Transformers library. Previously, I worked at fast.ai, where I helped develop the fast.ai library as well as the online book. Before that,
So like I can't figure out Hugging Face. I don't know if it's like a mental block that I have. But like when I go on there, I'm like, how do I download this shit? And it's like such a pain in the ass to figure it out. And like the search for shit on there is a real pain in the butt too. Like you got to know like what you're looking for. Like the exact names of it and all that stuff.
I was a math and computer science teacher in France.
I'm going to go make
Hi,
VTuber.
my name is Sasha and I'm a researcher at HuggingFace working on the ethical, environmental, and social impacts of machine learning models. Previously, I was a postdoctoral researcher at MILA, University of Montreal, and I also worked as an applied AI researcher for the United Nations Global Pulse. I've been involved in projects such as Code Carbon.
I think I used Hugging Face and Comfy together when I attempted to at one point last year. Now, like, I kind of like, I'm setting up like a Comfy UI server. I was like trying to set that up on there. But I was finding like, it wasn't liking my GPUs. It wasn't liking my GPUs.
Later to measure the carbon footprint.
Which is okay. Like I mostly got those to run, run LLMs on.
Learning.
But I wanted to have like when I'm not running an LLM on it, like I wanted to like use it. You know, I wanted to use it for other things.
Hi, I'm Merve, and I'm a developer advocate at HuggingFace. Previously, I was working as a machine learning engineer, building NLP tools and chatbots. Currently, I'm working to improve the hub and democratize machine learning.
Democratize machine learning.
Hello everyone, my name is Lucille, and I'm a machine learning engineer at HuggingFace. To tell you in 2 sentences who I am, I work on the development and support of open source tools, and I also participate in several research projects in the field of natural language processing.
I'll sit on her lap.
G'day there, I'm Lewis, and I'm a machine learning engineer in the open source team.
She's a secret villainess.
I'm passionate about developing tools for the NLP community, and you'll see me at many of Hugging Face's outreach activities. Before joining Hugging Face, I spent several years developing machine learning applications for startups and enterprises in the domains of NLP, topological data analysis, and time series. In a former life, I was a theoretical physicist.
Is that guy Australian or a New Zealander?
Where I researched particle collisions at the Large Hadron Collider in CERN.
Maybe he's not.
Hey, I'm Leandro, and I'm a machine learning engineer in the open source team at Hugging Face. Before joining Hugging Face, I worked as a data scientist in Switzerland
Australian.
and have taught data science at university.
We needed more introductions like that guy. Is there like a next? Is there a next? Let's go. Okay, natural language. My ex-wife is a New Zealander, and she would be pissed. She thinks, oh, what's that guy's name? Oh, shit. Why am I drawing a blank on his name? He was in A Beautiful Mind. Oh, Mind. Ron Howard directed that? That's crazy. Russell Crowe. Yeah. She says that he's a traitor. Should I like read this shit too or just like watch the video?
Welcome everyone. This presentation, automatically generated from the course material of Chapter 2, will walk you through...
Wait a second. Automatic? Wait a second. Wait a second. Wait a second. Did they basically just say they like... I'm turning down my music on my end. Did they just say they just had a AI make it for them?
Welcome everyone. This presentation, automatically generated from the course material of Chapter 2, will walk you through the key topics.
I do have like really bad ADHD, so maybe I will read it too. Yeah, that's a good idea.
Natural language.
I see. I missed that because of my ADHD.
Welcome everyone. This presentation, automatically generated from the course material of Chapter 2, will walk you through the key topics. Natural language processing, or NLP, is a field at the intersection of linguistics and machine learning.
It's warm because it's cold out there.
About understanding.
It is fucking freezing out there. Yeah, we got like 12 inches of snow, and like it's gonna be like it's not gonna get above the 10s in Fahrenheit. I think it was like 5 degrees high Fahrenheit today. I don't know what that is like in Celsius. It was fucking cold. It's -2 right now. The high tomorrow will be, wait a second, 1. What the fuck? How's it gonna get so high tomorrow? But then like Wednesday is gonna be like high 17, 15. And then like these are the days, like we won't get like 29 until Monday. I don't want to scooter to work. Oh yeah. Oh my gosh. Ooh, awful. Awful.
Individual words, but grasping the context in which they're used. NLP encompasses a wide range of tasks, from analyzing sentiment in reviews to generating text and even recognizing speech. Let's dive deeper into what makes NLP so powerful and challenging.
NLP.
In recent years, the rise of large language models, or LLMs, has transformed the NLP landscape. Models like GPT and Llama, trained on vast amounts of text data.
So the reason why I don't want to use like Llama and then prompt it to make an AI that I want to speak, because it's like not fucking stable at all. So I'd rather build one raw that's like just filled full of bullshit.
Can understand and generate human-like text.
I don't need a fucking LLM to
has moved us away
be able
from
to
building specialized models for specific tasks.
Tell me what the current politics is and
that can handle a wide range of language tasks.
In like Ethiopia.
Let's explore what makes LLMs so groundbreaking. Despite the advancements in NLP and LLMs, language
I'm watching a HuggingFace tutorial.
Processing remains a challenging task. Computers don't process information the way humans do, and language is inherently complex. Ambiguity,
I'm not really paying attention because this is like
sarcasm and humor are just a few of the hurdles that make this field so.
Okay, like we have a hard time processing sarcasm like in text also. Yeah, it's fucking cold out.
Intricate. We'll discuss how these challenges are being addressed and why they still persist. NLP involves a variety of tasks that help.
What if I train a model just on voice?
Language, from classifying entire sentences to identifying the grammatical structure of words.
I send in that.
These tasks are the building blocks
send in the
of NLP.
audio data
Text
along with the
generation,
fucking
translation and question answering are just a few examples of how NLP
along with the
is
text
applied
data
in real-world scenarios. Let's take a closer look at these tasks and their applications. Large language models are characterized by their immense scale, with millions to hundreds of billions of parameters. This scale enables them to perform a wide range of tasks without needing task-specific training. They can learn from examples provided in the prompt and even demonstrate emerging.
Yeah, I'm watching this make an LLM. The problem is I have like no like Python.
Let's explore what makes these models so versatile and powerful. While LLMs are incredibly powerful,
so I might be like skipping too far ahead on this.
They can hallucinate.
So I'm watching this for the first time, by the way,
with confidence and lack
because I didn't have any time during the day.
World, relying instead on statistical patterns. Biases in training data can also
I want
be
an AI that
and their context
hallucinates
windows, though improving,
70% of the time.
Additionally, these models require significant computational resources. Let's discuss these challenges and their implications. The advent of LLMs has shifted the paradigm in NLP, moving from specialized models to a single,
knowing what you don't know about a project is the first step.
Handle a wide range of tasks. This shift has made sophisticated language processing more accessible, but has also introduced new challenges in areas like efficiency, ethics, and deployment. Let's explore how this
I want an
change is
AI with
reshaping
no
the field
ethics.
and what it
I want
means
one
for
that will
future
hit
of
the big
NLP.
red button. Cold Garage. What the fuck is this fucker doing? Oh, turn off these iOS 26 settings. Can I like...
iOS 26 is...
I need to know this because I'm fucking hate iOS 26. Anyways. Ah! Did I get... There we go. NLP is a field of linguistics and blah, 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 blah. Raise large language models. Blah, 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 blah. Emerging abilities. Okay. And kind of these learned examples provided in the prompt. General capabilities. Yeah, I want to know like how you feed them and like what's a good way to feed them. Lack of true understanding. Yep. Blah, blah, blah. See the open and collab button at the top right and click on the Google Colab. You want an AI that will get its own brand channels to stream so it doesn't immediately get yours banned or filtered. That's probably a good idea. Like I did kind of set up like a channel, but so like if you have an account, you can like have several of them, and I was gonna make like a channel called BTD Garu BTD Garu VT, but maybe I can do like its own channel. Yeah. BTD Garu. Yeah. And I was going to use well, to start off, I was going to use this model. I was going to use this model right here for her. It's supposed to sound like Big Titty, but Big TD, BTD. The physics on this aren't very good. Anyways. Where does it jiggle? I guess it's okay. Anyways. Okay, in this section, we will look at transformer models. First tool from the transformer library, the pipeline function. Transformers models are used to solve all kinds of tasks across different modalities. What the fuck?
Modality.
Modalities. Modality, the fact, state, or quality of being. Okay.
Modality.
Modal. Of being modal. Okay, so. Wow. Don't define a word by using the same word. I mean, yeah. A tendency to conform to a general pattern or belong to a particular group or category. All right. Learning every day, baby. Including natural language processing. Okay. Computer vision, audio processing, and more. Here are some of the companies. Okay. The Transformer Library provides the functionality. The Model Hub contains millions of pre-trained models that anyone can download and use. You can also upload your own models to the hub. Before diving into how transformer models, like, do they want us to click up here? All right. Now, I've never like used like this before. For transformers, from transformers import pipeline, classifier pipeline, sentiment analysis classifier. I've been waiting for a Hugging Face course my whole life. All right. I hate this so much. I love the programmer attitude in that. All right. From transformer, from pipeline, like you press play on this shit. Like, what is this? Oh my gosh. What the fuck does all this shit mean? All right, let's go back. Hugging Face Hub is not limited to transfer models. Anyone can share any kind of models or data sets they want. Working with pipes. Yeah.
The pipeline function. The pipeline function is the most high-level API of the Transformers library. It regroups together all the steps to go from raw text to usable predictions. The model used is at the core of the pipeline.
I'm cranking my audio
But the
up.
pipeline also includes all the necessary preprocessing, since the model does not expect text but number, as well as some post-processing to make the output of the model human readable.
This will be on the test. Yes.
Let's look at the first example of the sentiment analysis pipeline. This pipeline performs text classification on a given input and determines if it's positive or negative. Here, it attributed the positive label on the given text with a confidence of 95%.
What does this mean?
You can pass multiple texts to the same pipeline, which will be processed and passed through the model together as a path.
So I guess like the label is positive, label negative. So when it gets like this text, it's gonna return. It wants you to return. Once it return the label positive, like the text positive on it for something that's positive sounding, and then negative for that's negative. That's kind of cool. That's kind of cool. Yeah.
The output is a list of individual results in the same order as the input text.
It'd be hard to like get someone there to like label all that shit. But maybe there's like someone out there that's already made this. Yeah.
Here, we find the same label and score for the first text, and the second text is judged negative with a confidence of 99.9%. The zero-shot classification pipeline is a more general text classification pipeline. It allows you to provide the labels you want. Here, we want to classify our input text along the labels education, politics, and business. The pipeline successfully recognizes it's more about education than the other labels.
Education.
With a confidence of 84%.
So this is the return. This is already when it went through, and these are what the, I guess like the, how close it got to these. So.
Moving on to other tasks, the text generation pipeline will autocomplete a given prompt. The output is generated with a bit of randomness, so it changes each time you call the generator object on a given prompt. Up until now, we've used the pipeline API with the default model associated to each task, but you can use it with any model. Use the pipeline API on a given prompt.
Pipeline.
Up until now, we've used the pipeline API with the default model associated to each task, but you can use it with any model that has been pre-trained or fine-tuned on this task. Going on.
Modal or model?
On the Model Hub, huggingface.co/models,
Models.
you can filter the available models by task. The default model used in our previous example was GPT-2, but there are many more models available, and not just in
That's
English.
negative.
Let's go back to the text generation pipeline and load it with another model, Distill GPT-2. This is a lighter version of GPT-2 created by the Hugging Face team. When applying the pipeline to a given prompt, we can specify several arguments, such as the maximum length of the generated text or the number of sentences we want to return, since there is some randomness in the generation.
All right.
Generating text by guessing the next word in a sentence was a pre-training objective of GPT-2. The fill mask pipeline is a pre-training objective of BERT, which is to guess the value of masked words. In this case, we ask...
I'm sorry. I'm not understanding a word he said, and it turned my subtitles off. I could not understand a word he said.
The default model used in our previous example was GPT-2, but there are many more models available, and not just in English. Let's go back to the text generation pipeline and load it with another model, Distilled GPT-2. This is a lighter version of GPT-2 created by the HuggingFace team. When applying the pipeline to a given prompt,
what is it?
We can speed by the HuggingFace team.
You see how he's pronounced hugging?
GPT-2. This is a lighter version of GPT-2 created by the HuggingFace team.
The Ugly Face team?
When applying the pipeline to a given prompt, we can specify several arguments, such as the maximum length of the generated text or the number of sentences we want to return, since there is some randomness in the generation. Generating text by guessing the next word in a sentence
he needs
was
an
the pre-training
enunciate
objective of GPT-2. The fill mask pipeline is a pre-training objective of BERT.
Not to toot my own horn, but I did like announcements in high school, and the teacher that was involved in that really, like, you know, instilled into me to enunciate my words.
Which is to guess the value of masked words. In this case,
professionally
we ask
accurate.
the two
Yeah.
most likely values for the...
I almost went the route of broadcasting. I almost did. I just need to use an adaptive language AI dub. Yeah.
Missing words according to the model, and get mathematical or computational as possible answers. Another task Transformer's model can perform is to classify each word in a sentence instead of the sentence as a whole. One example of this is named entity recognition, which is the task of identifying entities such as persons, organizations, or locations in a sentence. Here, the model correctly finds the person, Sylvain, the organization, HuggingFace, as well as the location, Brooklyn, inside the input text.
Brooklyn.
The grouped entities equal to arguments used to make the pipeline group together the different words linked to the same entity, such as hugging and face here.
Okay, sometimes he like enunciates entity well, and sometimes he doesn't.
Another task available with the pipeline API is extractive question answering. Providing a context and a question, the model will identify the span of text in the context containing the answer to the question. Getting short summaries of very long articles is also something the Transformers library can help with the summarization pipeline. Finally, the last task supported by the pipeline API is translation. Here, we use a French-English model found on the Model Hub to get the English version
is not
of our input
conductive
text.
to English pronunciation.
Here is a brief summary of all the tasks we've looked into in this video. Try them out through the inference widgets in the Model Hub.
They went over all this? Zero shot class. Start by tackling more quiet. What's a zero shot? Oh. 0, 1, 1. Yeah, so yeah, this one shot. What, zero shot? I thought this was called one shot. One shot classification. Okay. One shot classification is machine learning where models learn, recognize. Okay, let's go to Google. I really need to change my search to Google on this one because Google's like, their AI is way better. Okay. One shot versus zero shot. shot classification. I'm doing this because I want to. Anyways. Zero shot asks AI to categorize data without any prior examples, relying solely on its pre-trained knowledge. Contrast, one-shot classification provides the model with a single example of a new category to improve accuracy. Oh, okay. Zero shot is best for general tasks, while one shot is better for specific formatting. Interesting. So how do you train on that? No training. Wait a second. No training models are What? I don't get it. So you just don't train it? All right. Anyways. Yeah. Key difference: zero shot equals zero examples. One shot equals one example. One shot generally offers better, more consistent accuracy on new complex tasks. Yeah. The better question is, how do you categorize your baselines for training data to feed it? Here's the thing, like, I thought, like, basically these LLMs were, how do I put it? Were like autoencoders. That's what I thought. But maybe my like idea, maybe that's not it. Like you want to train the input to be the output, right? Or yeah, you want the output, sorry. You want to train the output to be the input. Yeah. Did they go over mask filling? All of this trade browser interference providers, which is available on HuggingFace, where you can play the model directly on page, input custom text, and watching the model's process input data. All right, fill mask. This course will teach you about mask. Okay. Name any recognition. I think this is going like way too like deep into this shit that I don't really want to go into. Summarizer. So I guess like if you had like a big ass thing, be like, summarize this shit. Summarize it even more. Image classification. One powerful application of transfer models is the ability to combine and process data from multiple sources. This is especially useful when you need to search across multiple databases and repositories, consolidate. Searches for information across databases and multiple modalities like text and image. All right. Teach us, Sensei. We're taking things up a notch here. This selection in detailed and technical, so don't worry if you don't understand everything right away. This is where I hate it the most in this section. Let's take a look at architecture or transformer. Like, I can't even really understand the transformer. Yeah. The transformer architecture was introduced in 2017. The focus of the original research was on translation tasks. This was followed by the introduction of several influential models, including, it's written from the perspective of a massive software engineer enthusiast, for somebody just as adept instead of being comprehensive for the sake of universal adaptation. I think you're kind of right on that. Like, they do want you to be like, have like some of the stuff, but they're so like deep in bed with this stuff here. They don't really understand, like, they don't understand like how to dumb it down, so to speak. GPT, the first pre-trained transfer model. BERT, another large pre-trained model. This one designed to produce better summaries of sentences. GPT-2, an improved and bigger version of GPT that was not immediately publicly released due to ethical reasons. Bitch. Multitask focused implementation of the T5 GPT-3, even bigger version of GPT-2 that is able to perform well on a variety of tasks without the need for fine-tuning. Zero-shot learning. Okay, so the fine-tuning is the zero-shot learning. All right. Instruct GPT. A version of GPT-3 that was trained to follow instructions better. Listen to me, bitch. Llama, a large language model given by Facebook. Mistral, a 7 billion parameter language model that outperforms Llama 2, 13 billion across all evaluated benchmarks. Okay, blah, blah, blah. What's this small? A state-of-the-art language model, not any longer. 2024, baby. 135 million to 1.7 billion parameters. This achieves impressive performance despite its compact size and unlocking new possibilities for mobile and edging devices. Yeah. Transformers are language models. All the transformer models above have been trained as language models. This means they have been trained on large amounts of raw text in a self-supervised fashion. Self-supervised learning is a type of training in which the objective is automatically computed from the inputs of the model. That means that humans are not needed to label the data. What is this, an autoencoder? This type of model develops a statistical understanding of the language it has been trained on, but it's less useful for specific practical tasks because of this. The general pre-trained model then goes through a process called transfer learning or fine-tuning. During this process, the model is fine-tuned in a supervised way, that is, using human annotated labels or given a task. From their perspective, laymen probably haven't earned the required understanding of their field, so it makes sense that they would treat this like a published research paper before a tutorial. It's kind of like a class, like, you know, like a good place to go, like, and you don't need to know like a whole bunch about AI. It's like the Stanford University AI class. University AI course. Now, like a lot of the old ones are gone, or it's like harder to find. Yeah, this is 2025. He's back there. Yeah, so here's a 2018. They had like one for like 2015. So Andrew NG, I call him NG, is probably he actually has like courses too. Andrew NG. So like he was on Lex Freeman. He had a thing like went through papers and stuff. But I don't know if this is his class or I don't think it is his. It might be like gone now. Andrew Karpathy, or is it Karparthy? He's a good one too. Yeah, they're large, but they have them all online.
Hello, everyone.
Right? Yeah. But like, you gotta start somewhere with a lot of these. So maybe I should save like this playlist. Oh, I guess I'll have to remember it's a Nyata Neko channel. Yeah. So maybe this will be like good. But like the Stanford, like, okay, Stanford AI class. They had like, wait a second. What is it called? CovNet JS. Is it still available? Is it ComNet? Okay. Getting started quickly. Discuss documentation for all specifics. So like, this is all like done on JavaScript. Tutorial. I thought he had like a link to like the classroom in this. But yeah, nice little tools. Like this really helped me understand like AIs more than anything. And he wrote it all in JavaScript. CovNet JS, blah 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 blah. Full documentation found here. Getting started. I was hoping one of these would go to his classroom page, but he's not. I think he's at OpenAI now. He might either be at OpenAI or he's working for Tesla. One of the two. All right, so another is masked language modeling. So I was kind of thinking about that too. Yeah, mask. I was like, how am I going to add like someone's name, like in general, in which the model predicts a masked word in the sentence? Yeah, it's really hard to really know where to start. Sometimes in places thriving in a lane of exponential growth. Yeah, because like, here's the thing too, like, let's say you're trying to look for a certain thing, right? You're like, what do they call? What do they call this? Hold on a second. Okay, so let's say you want to have like voice isolation, right? Like an AI that will just isolate the voice and that's all you have. Well, it's not really called voice isolation. It's like the field is it's called like voice remover. Which like you can just like put that and you can make it so it does it on a separate track. Like the voice and the other audio. And it's like, okay, so it's voice remover, but it covers the same as just voice isolation. But if you like, maybe now, like if you type in like voice, like isolation, like you can find stuff that involves that. But like, let's see if that works. Okay, like voice isolation. I don't know. Open source AI. Okay, so that has a voice remover. So yeah, it will do that. Like human body part, you can like, if you're wanting to do like look for human body parts or human body part labeler or whatever, like, or human joint position labeler, like you would not find anything because it's all under the name of like human pose. Everybody calls it pose. Transformers are big models. Where's Distilbert? Yay! So they found out like these large ass fucking models, their carbon footprint. Like a lot of them aren't like a lot of the like the I guess like the neurons inside of it don't get used. And so they're like overly complicated. And a lot of them like just doesn't get used because the larger the content, like the less like the initial state of your weights, you don't have to worry about the initial state of your weights as much. Why are they talking about carbon emissions? No one gives a shit about carbon emissions, okay? What is transfer learning? All right, let's do this. I was hoping to build models and shit.
What is transfer learning? The idea of transfer learning is to leverage the knowledge acquired by a model trained with lots of data on another task. The model A will be trained specifically for task A. Now let's say you want to train model B for a different task. One option would be to train the model from scratch. This could take lots of computation, time, and data. Instead, we could initialize model B with the same weights as model A, transferring the knowledge of model A on task B. When training from scratch, all the model's weights are initialized randomly.
We got time.
In this example,
and data.
We are training a BERT model on the task of recognizing if two sentences are similar or not. On the left, it's trained from scratch.
This is where you groom your... when you're fine-tuning, also known as grooming your model.
On the right, it's fine-tuning a pre-trained model. As we can see, using transfer learning on the pre-trained model yields better results. And it doesn't matter if you train longer. The training from scratch is capped around 70% accuracy, while the pre-trained model beats the 86% easily. This is because pre-trained models are usually trained on large amounts of data that provides the model with a statistical understanding of the language used during pre-training. In computer vision, transfer learning has been applied successfully for almost 10 years.
Church, holy shit, that looks like a fucking medieval castle.
Models are frequently pre-trained on ImageNet, a dataset containing 1.2 million of photo images.
I think I downloaded this ImageNet.
Each image is classified by one of 1,000 labels. Training like this on labeled data is called supervised learning.
Supervised.
In natural language processing, transfer learning is a bit more recent. A key difference with ImageNet is that the training is usually self-supervised.
Okay, transfer learning is not really recent. It's not.
Which means it doesn't require human annotation for the labels. A very common pre-training objective is to guess the next word in a sentence, which only requires lots and lots of text. GPT-2, for instance, was pre-trained this way using the content of 45 million links posted by users on Reddit. Another example of
that's
self-supervised training objective is to predict the value of randomly masked words, which is similar to fill-in-the-blank tests you may have done in school. BERT was pre-trained this way using the English Wikipedia and 11,000 unpublished books. In practice, transfer learning is applied on a given model by
Wikipedia, Reddit. Yeah, that's gonna be a real good AI with no opinion.
That is, its last layers focus on the pre-training objective and replacing it with a new, randomly initialized head suitable for the task at hand. For instance, when we fine-tuned the BERT model earlier,
we trained our AI on Blue Sky
and replaced it with a classifier with 2 outputs, since our task had 2 labels.
2 labels?
To be as efficient as possible, the pre-trained model used should be as similar as possible to the task it's fine-tuned on. For instance, if the problem is to classify German sentences, it's best to use a German pre-trained model. But with the good comes the bad. The pre-trained model does not only transfer its knowledge, but also any bias it may contain. ImageNet mostly contains images coming from the United States and Western Europe. The models fine-tuned with it usually will perform better on images from these countries.
Yeah.
OpenAI also studied the bias in the prediction of its GPT-3 model, which was pre-trained using the guess the next word objective. Changing the gender of the prompt from he was very to she was
how you make
very.
What if you get all the streamers as a stream and get all their data and then throw it into an AI.
Changed the predictions from mostly neutral objectives to almost only physical ones. In the model card of the GPT-2 model, OpenAI also acknowledges its bias and discourages its use in systems that interact with humans.
SNL, what is this? Steering. It just turns into a worse Fillion. Where is Fillion? What is this? Hold on a second. Pre-training is the active training model from scratch. Yay! Base model, large corpus, days training. Pre-training is usually done on very large amounts of data, therefore requires very large corpus of data, and training can take up several weeks. I might take like well, shit. Never mind, I don't want to do that. I want to make my own model. Since pre-training model was already trained on lots of data, the fine-tuning requires way less data to get decent results. For the same reason, the amount of time, blah, 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 blah. Shut the fuck up. They have a scene outro transition, like they're going to have a part 2, but it just ends. Yeah, they just like put them all in these sections. They probably decided to do it this way later on or something. One example could be leverage a pre-trained model trained on the English language and then fine-tune it on an RVIX corpus, resulting in a science research-based model. The fine-tuning will only require a limited amount of data. The knowledge of pre-trained model is required transferred, hence the term transfer learning. I know I should like try to get all like the, what are those like fandom, like fan-made lore for, I forget what that shit's called, but like just like get all that degeneracy into the AI as much as possible. The fine-tuning model therefore has lower time data, financial, environmental costs. Yes. General transformer architecture. Teach me, daddy.
Let's study the transformer architecture.
This is louder.
This video is the introductory video to the encoders, decoders, and encoder-decoder series of videos. In this series, we'll try to understand what makes a transformer network, and we'll try to explain it in simple, high-level terms. No advanced...
Now, like, I don't know if anybody's done this, but like, what if you started, like, you train one day at like kindergarten level? Do people start reading in kindergarten? Maybe it's like first grade. Like first grade, like reading, or like you start like the reading with like kids books, right? And then like then you move up to like kindergarten and then first grade, and then like, you know, second, third, fourth, fifth. You just kind of like level it all up. I wonder if anybody's kind of done anything like that.
Understanding of neural networks is necessary, but an understanding of basic vectors and tensors may help. To get started, we'll take up this diagram from the original transformer paper entitled Attention is All You Need by Vaswani et al.
Attention's all you need.
Here, we can leverage only some parts of it according to what we're trying to do. We won't dive into the specific layers building up that architecture, but we'll try to understand the different ways this architecture can be used. Let's first start by splitting that architecture into two parts. On the left, we have the encoder, and on the right, the decoder. These two can be used together, but they can also be used independently. Let's understand how these work. The encoder accepts inputs that represent text. It converts this text, these words, into numerical representations. These numerical representations can also be called embeddings or features. We'll see that it uses the self-attention mechanism as its main component. And we recommend you check out the video on encoders specifically to understand what is this numerical representation, as well as how it works. We'll study the self-attention mechanism in more detail, as well as its bidirectional properties. The decoder is similar to the encoder. It can also accept text inputs. It uses a similar mechanism as the encoder, which is the masked self-attention as well. It differs from the encoder due to its unidirectional feature, and is traditionally used in an autoregressive manner.
Autoregressive.
Here too, we recommend you check out the video on decoders especially to understand how all of this works.
Okie dokie, artichoke.
Combining the two parts results in what is known as an encoder-decoder, or a sequence-to-sequence transformer. The encoder accepts inputs and computes a high-level representation of those inputs. These outputs are then passed to the decoder. The decoder uses the encoder's outputs alongside other inputs to generate a prediction. It then predicts an output, which it will reuse in future iterations, hence the term autoregressive. Finally, to get an understanding of encoders decoders as a whole, we recommend you check out the video on encoder decoders.
Ooh. Encoder left encodes, receives input, builds representations, features. That means that the model is optimized to require understanding from the input. The decoder uses encoders representation features along with the other inputs to generate a target sequence. This means that the model is optimized for generating outputs. All right. These parts can be used independently depending on the task. Encoder-only models, okay, good for tasks that require understanding of the input, such as sentence classification and named entity recognition. All right. Decoder-only models, good for generative tasks such as text generation. All right. Encoder-decoder models or sequence-to-sequence models, good for generative tasks that require an input such as translation or summarization. Huh. But like to train it, do you need both? Yeah. A key feature of transformer. Okay, attention layers. A key feature of transformer models is that they build with special layers called attention layers. In fact, the title of the paper introduces transformer architecture was "Attention is all you need." That's like the most famous fucking paper now. We will explore the details of attention layers later in the course. For now, all you need to know is that this layer will tell the models to pay specific attention to certain words in the sentence you passed it, and more or less ignore the others, bitch, when dealing with the representation of each word. To put this, I was trying to make this like easy to read. All right. This will be like, I feel like, ask Hugging Chat. To put this into context, consider the task translating text from English to French. Given the input, you like this course, a translation model will need to also attend the adjacent word you to get the proper translation for the word like, because in French, the verb like is conjugated differently depending on the subject. The rest of the sentence, however, is not useful for the translation of that word. In the same vein, when translating this, the model will also need to pay attention to the word course because this translates differently depending on the sentence, depending on whether the associated noun is masculine or feminine. Again, the other words in the sentence will not matter for the translation, of course. With more complex sentences and more complex grammar rules, the model will need to pay special attention to the words that might appear farther away in the sentence to properly translate each word. So it will translate you like this course into you like this course. That was my really bad French accent. All right. Ha ha ha, you like this course? Ha ha ha. The same concept applies to any task associated with the natural language. Blah, 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 blah. Now you have an idea of what attention layers are all about. Let's take a closer look at the transformer architecture. Okay. Yeah. Let's read this. All right. Oh, shit. The transformer architecture was originally designed for translation. During the training, the encoder receives input sentences in in a certain language, while the decoder receives the same sentences in the desired target language. Interesting. In the encoder, the attention layers can all use the words in a sentence, since, as we just saw, the translation of a given word can be dependent on what is after as well as before it in the sentence. Okay. So, yeah. It needs to look at the whole sentence, not just single words, right? The decoder, however, works sequentially and can only pay attention to the words in the sentence that it has already translated. So only the words before the word currently being generated. For example, when we have predicted the first 3 words of the translated target, we give them to the decoder, which then uses all the inputs of the encoder to try to predict the 4th word. What? So the encoder receives inputs, so the sentences, in a certain language, while the decoder receives the same sentence in the desired target language. Okay. In the encoder, the attention layers can use all the words in a sentence, since, as we just saw, the translation of a given word can be dependent on what is after as well as before in the sentence. The decoder works sequentially and can only pay attention to the words in the sentence that it has already translated. Okay, so only the words before the word currently being generated. For example, when we have predicted the first 3 words of the... Yeah, okay. All right. To speed things up during training, when the model has access to the target sentences, the decoder is fed the whole target, but it is not allowed to use future words. If it had access to the word position 2 when trying to predict the word at position 2, the problem would not be very hard. What? Decoder, okay. To speed things up during the training, the decoder is fed the whole target, but is not allowed to use the future words. If it had access to the word at position 2 when trying to predict the word at position 2. Oh, yeah. Okay. Yeah, because it would just, yeah. For instance, when trying to predict the 4th word, the attention layer will only have access to the words in the positions 1 to 3. Yeah. It'd be like future sight or whatever if it had 4 already somehow. The original transformer architecture looked like this, with the encoder on the left and decoder on the right. Whee! That's that, Mr. That's That. Should I take a picture of this? Maybe I want to bring it up here while it's reading about it. Seems like I might reference it. All right. Maybe I can do... Note that the first attention layer in the decoder block pays attention to all past inputs to the decoder, but the second attention layer uses the output of the encoder. It can thus access the whole input sentence to best predict the current word. This is very useful, and as a different language can have grammatical rules that put the word in different order, or some context provided later in the sentence may be helpful to determine the best translation of a given word. The attention mask can also be used in the encoder decoder to prevent the model from paying attention to some specific words. For instance, the special padding word used to make all the inputs of the same length, then batching together sentences. I didn't know they had that. They have masks? All right, they have padding for the words? Or sentences? Were used to make all the inputs the same length when batched together sentences. Okay. Okay, interesting. As we dive into transfer models in this course, you'll see mentions of architectures and checkpoints as well as models. These terms have all slightly different meanings. Architecture, this is the skeleton of the model, the definition of each layer and each operation that happens within the model. Checkpoints, these are weights that will be loaded in a given architecture. All right, model, this is an umbrella term that isn't as precise as architecture or checkpoint. It can mean both. This course will specify architecture or checkpoints when it matters to reduce ambiguity. All right. So I thought they said there's like videos on the encoder and decoder. Oh, they're right here. So like, wait a second. So this one was the, I guess I'll go here.
In this video, we'll study the encoder architecture. An example of a popular encoder-only architecture is BERT, which is the most popular model of its
What about Ernie?
That's
so a decoder only architecture would be Ernie.
We'll start by understanding how it works. We'll use a small example using 3 words. We use these as inputs and pass them through the encoder. We retrieve a numerical representation of each word. Here, for example, the encoder converts those 3 words "Welcome to NYC" in these 3 sequences of numbers. The encoder outputs exactly 1 sequence of numbers per input word. This numerical representation can also be called a feature vector or a feature tensor.
Tensor.
Let's dive in this representation. It contains 1 vector per word that was passed through the encoder. Each of these vectors is a numerical representation of the word in question.
All right.
The dimension of that vector is defined by the architecture of the model. For the base BERT model, it is 768. These representations contain the value of a word, but contextualized. For example, the vector attributed to the word "to" isn't the representation of only the "to" word.
Yeah.
It also takes into account the words around it, which we call the context.
Okay.
As in, it looks to the left context, the words on the left of the one we're studying, here the word "welcome," and the context on the right,
jungle, baby.
Here the word "NYC," and it outputs a value for the word given its context. It is therefore a contextualized value. One could say that the vector of 768 values holds the meaning of the word within the text.
Yeah.
It does this thanks to the self-attention mechanism. The self-attention mechanism relates to different positions or different words in a single sequence in order to compute a representation of that sequence. As we've seen before, this means that the resulting representation of a word has been affected by other words in the sequence.
Oh.
We won't dive into the specifics here, but we'll offer some further readings if you want to get a better understanding at what happens under the hood. So when should one use an encoder? Encoders can be used as standalone models in a wide variety of tasks.
Standalone.
For example, BERT,
models.
arguably the most famous transformer model, is a standalone encoder model. And at the time of release, it'd be the state-of-the-art in many sequence classification tasks, question answering tasks.
All right. I don't like the term state of the art. I just think I've read so many papers of them saying that whatever they made is state of the art. It's just so pretentious, and it just makes me want to, like, I don't know. It just hearing the word just yeah.
Tasks and masked language modeling, to only cite a few. The idea is that encoders are very powerful at extracting vectors that carry meaningful information about a sequence.
They say it's state of the art, but the week after that, the next one's the state of the art. So what the fuck, dude? Like, seriously, don't say it's state of the art.
This vector can then be handled down the road by additional neurons to make sense of them. Let's take a look at some examples where encoders really shine. First of all, masked language modeling, or MLM. It's the task of predicting a hidden word in a sequence of words. Here, for example, we have hidden the word between my.
I was looking for the word pet peeve. I haven't been running on very much sleep lately. That's my pet peeve. Don't use the word state of the art in your papers. It just fucking, like, like, if I was like to grade a paper and they use the term state of the art, our model is state of the art, and blah 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 blah. I think I'd automatically drop it a letter grade.
And is. This is one of the objectives with which BERT was trained. It was trained to predict hidden words in a sequence.
Oh yeah.
Encoders shine in this scenario in particular, as bidirectional information is crucial here. If we didn't have the words on the right, is Sylvain and the dot, then there is very little chance that BERT would have been able to identify name as the correct word. The encoder needs to have a good understanding of the sequence in order to predict a masked word, as even if the text is grammatically correct, it does not necessarily make sense in the context of the sequence. As mentioned earlier, encoders are good at doing sequence classification. Sentiment analysis is an example of sequence classification.
Yeah, we saw this earlier.
The model's aim is to identify the sentiment of a sequence. It can range from giving a sequence a rating from 1 to 5 stars if doing review analysis, to giving a positive or negative rating to a sequence, which is what is shown here. For example, here, given the two sequences, we use the model to...
I can kind of see how they use this to train out certain languages or certain sentences. Let's say you don't want it to say a certain person wasn't wrong. You might have like, you might make it negative, so you train it out of there.
To compute a prediction and to classify the sequences among these two classes, positive and negative. While the two sequences are very similar, containing the same words, the meaning is entirely different, and the encoder model is able to grasp that difference.
Hell yeah, brother. Decode.
In this
Decode
video,
these nuts.
we'll study the decoder architecture. An example of a popular decoder-only architecture is GPT-2. In order to understand how decoders work, architecture is GPT-2. Decoder architecture.
Oh, GPT-2 is decoder-only
architecture is GPT-2. In order to understand how decoders work, we recommend taking a look at the video regarding encoders. They're extremely similar to decoders. One can use a decoder for most of the same tasks as an encoder, albeit with generally a little loss of performance. Let's take the same approach we have taken with the encoder to try and understand the architectural differences between an encoder and a decoder. We'll use a small example using 3 words. We pass them through the decoder.
Decode this.
We retrieve a numerical representation for each word.
All right.
Here, for example, the decoder converts the 3 words "Welcome to NYC" in these 3 sequences of numbers. The decoder outputs exactly 1 sequence of numbers per input.
So I don't understand how you're feeding it. Are you feeding these things in like one at a time and then it comes out, or what? Like
word. This numerical.
Or do you like decoder? Wait a second. Why are these arrows going this way? Wait, let's go back. I was thinking at the same time that he was talking.
Encoder and a decoder. We'll use a small example using 3 words. We pass them through the decoder. We retrieve a numerical representation for each word.
Okay.
Here, for example, the decoder converts the 3 words welcome to NYC in these 3 sequences of numbers.
Okay.
The decoder outputs exactly 1 sequence of numbers per input word. This numerical representation can also be called a feature vector or a feature type.
Yes.
Let's dive in this representation. It contains 1 vector per word that was passed through the decoder. Each of these vectors is a numerical representation of the word in question. The dimension of that vector is defined by the architecture of the model.
Wait a second, is it?
The dimension of
is defined by the architecture. Okay. So you can tell like how big it's gonna get. All right.
that vector is defined by the architecture of the model.
Yeah, all right.
Where the decoder differs from the encoder.
Because like you don't know like how big these are gonna be. Yeah. Where the decoder differs from the encoder is principally as a self-attention mechanism.
Is principally with its self-attention mechanism. It's using what is called masked self-attention. Here, for example, if we focus on the word to, we'll see that its vector is absolutely unmodified by the NYC word. That's because all the words on the right, also known as the right context of the word, is masked.
How do you know? Wait a second. He said, as you can see.
Self-attention.
Wait a second. So 2 is like this. Okay, so 2 is this, right? And then I guess he put the attention thing in there, and then basically it didn't change. Okay, so now it checks this, and the 2 just stays the same.
Is absolutely unmodified by the NYC word.
Okay.
That's because all the words on the right, also known as the right context of the word, is masked. Rather than benefiting from all the words on the left and right, so the bidirectional context, decoders only have access to a single context, which can be the left context or the right context. The masked self-attention mechanism differs from the self-attention mechanism by using an additional mask to hide the context on either side of the word. The word's numerical representation will not be affected by the words in the hidden context. So when should one use a decoder? Decoders, like encoders, can be used as...
This is kind of complicated in fucking ways to train this shit. I'm just used to like feeding data in and then it popping shit out.
Standalone models. As they generate a numerical representation,
and then
they can also
they're doing
be used
this,
in a
they're doing this masking shit. Like what the fuck?
wide variety of tasks. However, the strength of a decoder lies in the way a word can only have access to its left context. Having only access to their left context, they're inherently good at text generation, the ability to generate a word or a sequence of words given a known sequence of words. This is known as causal language modeling or natural language generation.
Yeah.
Here's an example of how causal language modeling works. We start with an initial word, which is my. We use this as input for the decoder.
Say my name.
The model outputs a vector of numbers, and this vector contains information about the sequence, which is here a single word. We apply a small transformation to that vector so that it maps to...
So wait a second. The model outputs a vector of dimension 768. Is this per like word?
Numbers. And this vector contains information about the sequence, which is here a single word. We apply a small transformation to that vector so that it maps...
That's a shit ton of dimensions.
...to all the words known by the model, which is a mapping that we'll see later, called a language modeling head. We identify that the model believes that the most probable following word is name. We then take that new word and add it to the initial sequence. From my, we are now at my name.
So I think you're taking the output of it. So you put my, and then this is the output, and then you tack it on. And then like tack it on. So I guess this is like the idea that this is like autocomplete.
Where the autoregressive aspect comes in.
Yeah.
Autoregressive models reuse their past outputs as inputs in the following steps. Once again, we do the exact same operation. We cast that sequence through the decoder and retrieve the most probable following word.
So this is like after it's already trained, right? They're not going over like how it's trained. This is like how it works when it's already fucking complete.
In this case, it is the word is. We repeat the operation until we're satisfied. Starting from a single word, we've now generated a full sentence. We decide to stop there, but we could continue for a while. GPT-2, for example, has a maximum context size of 1024. We could eventually generate up to 1024 words, and the decoder would still have some memory of the first words in the sequence.
Sorry. How Transformers solve okay, like, what are we gonna build this shit?
This presentation, automatically generated from the course material, will walk you through the key topics.
This guy sounds British. He's British.
Discussed in the document.
British.
Let's begin. In this section,
it sounds like that guy kind of sounds like you know, the eating chips guy. He kind of sounds like that guy.
Explore how transformers solve various tasks, focusing on language models, but also their applications beyond text. We'll also touch on the LLM course documentation, which provides an interactive experience.
Okay. I have ADD. So is it eating chips? No, it's not this guy. Okay. Who is that guy? Computer chips? Oh, no. Why eat computer chips? Wait a second. Why should we eat computer chips? Oh my gosh, computer chips in your brain. I thought it was eating chips. Holy shit. Okay, who's the guy? All right. Google, help me. Who is the VTuber that pretends to eat computer chips? No, I meant YouTuber. VTuber. No. YouTuber. He is a tech. Who is the tech? How about tech tuber? Tuber. Yeah. He pretends to take a bite to bite computer chips. Yeah. No. It's none of these guys. Oh my gosh. You think they would know. I don't remember the guy's name. I don't remember his channel. Like, I'm subscribed to it. It's probably like right here. Yeah. But he does his own shit now. Anyways. Why'd I get on that subject?
Experience to help you get started. Transformer models
because this guy's voice
revolutionized natural language processing. We'll delve into how language models work, the different types available, and their applications in text generation, classification, token classification, question answering, summarization, and translation. Language models are designed to understand and generate human language by learning statistical patterns and relationships between words. They predict word probabilities based on context, enabling them to generalize to various natural language processing tasks. There are three main types of language models: encoder only, decoder only, and encoder-decoder. Encoder-only models like BERT are great for understanding text, while decoder-only models like GPT excel at text generation. Encoder-decoder models like T5 combine both approaches for sequence-to-sequence tasks.
Sequence-to-sequence tasks?
Text generation involves creating coherent and contextually relevant text based on a prompt. GPT-2, a decoder-only model, is a prime example. It uses byte pair encoding and positional encodings to generate text, making it highly effective for this task. Text classification assigns predefined categories to text documents. BERT, an encoder-only model, is widely used for this task. It employs word piece tokenization and special tokens like SET and CLS to differentiate between sentences and capture overall text representation.
All right.
Token classification involves assigning labels to each token in a sequence, such as in named entity recognition. BERT can be adapted for this task by adding a token classification head, which is a linear layer that predicts labels for each token. Question answering requires finding answers within a given context. BERT can be used for this task by adding a span classification head, which predicts the start and end positions of the answer in the text.
All right.
Summarization involves condensing longer text into a shorter version while preserving key.
Potato. Potato tech? Tech potato. It's this guy. Getting an upgrade.
One of my three key technologies to look for in the semiconductor industry today is how we're going to connect
Key information. Encoder-decoder model.
Is that the same guy?
Encoder-decoder models like
All right. I'm going to be the first comment. Bro sounds like the tech potato dude. Like the tech potato. Yeah. Ah.
like BART and T5 are ideal.
I wonder if he did it
for this task.
Because, okay, the guy's like,
they are
the tech potato guy, like he used to be like a writer. I think he was like a writer for certain magazine, but he has his like PhD in this shit. And like, it's like, it is like bare metal, like PhD. It's not like, it's more on like the chip side, right? That's why it's tech potato. And then it shows like he has a sticker like a potato eating a chip, right? Ha 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 ha. Anyways.
Trained using text infilling corruption, which teaches the model to predict missing tokens. Translation converts text from one language to another while preserving meaning. Encoder-decoder models like BART and T5 are well suited for this task. BART adapts to translation by adding a separate encoder to map source language to target language. Transformers are not limited to text. They can also handle other modalities like speech, audio, and images. We'll briefly explore how transformers are applied to these domains. In speech and audio.
So like the one that I want to build is I want to take in video, maybe even like audio too. Yeah, audio. Yeah. What if it takes an audio and then like has a response in text.
Transformers.
I want to do video also, so it can kind of, or like not video, but like send in pictures also at the same time, so it can kind of like give context to what it's looking at.
Like Whisper are used for automatic speech recognition. Whisper is an encoder-decoder model pre-trained on a massive dataset of labeled audio data, enabling zero-shot performance across many languages and tasks. In computer vision, transformers like Vision Transformer, VIT, and ConvNext are used for image classification. Other models like DETA, Mask2 Former, and GLPN handle tasks such as object detection, segmentation, and depth estimation.
Yeah, baby.
Vision Transformer, VIT, processes images by splitting them into patches and using a CLS token to capture the overall image representation. Position embeddings are added to maintain patch ordering before passing them through the transformer encoder. ConvNext is a modern convolutional neural network. It is used for image classification and combines the strengths of convolutional layers with modern network architectures. Now, go check out the LLM course material. It provides an interactive experience to help you understand model architectures and their applications. By grasping common patterns, you can adapt existing models to your specific needs and tasks.
Do it. Do they want us to do it right now? Hello. Hello. How you doing? Transformers, what do? You learned about natural language processing, speech and audio computer vision tasks, and some important applications to them. This page will look closely at how models solve these tasks and explains what's happening under the hood. I couldn't be better. I couldn't be better. If I was any better, I'd have to go to the loony bin. There are many ways to solve a given task. Some models may implement certain techniques or even approach the task from a new angle. But for transformer models, the general idea is the same. Owing to its flexible architecture, most models are a variant of an encoder, a decoder, or an encoder-decoder structure. Before diving into specific architectural variants, it's helpful to understand that most tasks follow a similar pattern. Input is processed through a model and the output is interpreted for a certain task. The difference is how the data is prepared. Okay, I thought they were, what is this? Explain how it evolved. We'll cover the following models for their corresponding tasks. What is this? The audio classification. Angry person. Do I have to click this shit? What is this? I didn't know this was going to be like a full-on fucking course. I just want to like start building this shit. This kind of looks like this looks like a Whisper. Was it Whisper? Oh yeah, Whisper. That is Whisper. Should I read this shit? Let's read this shit. I guess I could have clicked on these, but I'm not going to. Before you go further, it's good to have some basic knowledge of the original transformer architecture. Knowing how encoders and decoders and intention work will aid you in understanding. Check out the previous section. Well, what the fuck, dude? Like, we don't just like jump right into this. Yeah, I want to write my own. I've been kind of gathering data to write my own. I want to have like a companion, not unlike Neurosama. I don't know why I didn't like hop onto this train like years ago. I probably thought like, I don't know. I think I'll start off as like a PNG and then kind of move up. I was trying to build like the interface in which it would like talk, but yeah, I didn't get to that part yet. I don't know, like I might have to switch my like streaming PC and my my work PC. That's what I'm thinking I might have to do. Well, I mean, like, okay. Now, I don't know, like, if he took bits and pieces of other people's code, but, like, oh, yeah, like, you can have, like, audio come out and stuff like that. But, like, having her mouth move, yeah, like, or, like, to have her, like, give her control of, like, the outputs. Like, how do they make the mouth move? But now there's, like, I think there's, like, let's go to my GitHub. Keep on yelling at me about this. All right. Holy shit, what do I have here? What do they call it? I forked it. Track anything, audio word finder. Oh, these are probably some of these are my own things. I'm not seeing it. Do. Test go packages, chat downloader. I don't think it's this. AI diffusion, chat downloader, that's mine. STT server, that was mine. Where's my forked? There we go. I forked them? Is it this art? I think this might be it. Yeah, that AI contains the soul within the AI waifu virtual character to bring them into your worlds. So I think this might take advantage of Live 2D. Yeah. Do they already have shit on there? Yeah, I stumbled upon this. So I think I might try, like, heavily inspired by Neurosama. So I don't know, like, how Vettel, I don't know how he gave the inputs to it. Maybe he had something fake a camera. You know, like, I don't, you know, like made like a fake camera, so to speak, to have it kind of give the outputs or whatever. I don't know. He must have hacked it or something. I was thinking about going here. Cause like, so like you put the camera in here and then it uses like, this is like the pipeline. So the tracking quality, like you give it this. So what this does is take it in there and then it pops out the output. So I don't know if he made like a, tracking type, only hand tracking. We can do like the hand and face, but somehow, okay, so here, hold on a second. Now this might be upside down. Yeah, let me try this. I have my camera up, so like only face. There we go. Camera on. Does it see me? It's not seeing me. Oh, wait a second. That's the wrong one. There we go. Let me try this one. It's not seeing me. Just do it, bitch. Fuck. All right. Important. It's not seeing me. I guess it's not working right now. Right now, it takes it from my iPhone. And yeah, it takes it from my iPhone. But yeah, I don't know how he does it. So there's like other people that done it too, but they're like, I'm not gonna go into detail how I did this, because of course they're not going to, because they don't want to, you know, have a bunch of other competitors in it. So I don't know if this is like just, maybe I can make it so this is the background or something. I don't know. It'd have to be a separate window. Yeah. I'd have to like really dive into this. So, but I have a separate streaming PC. I think that's what I'm going to do. I think I'm going to switch my work PC in with my streaming PC, because I'm going to need, if I'm doing this, if I'm doing this, I'm going to need to have like a multiple GPUs. I'm thinking. No, I gotta. So I say work PC. I guess I could say production PC. This is my production PC. So I clip VTubers too, and sometimes I clip videos for my own channel. I haven't like, I make videos, but I haven't done it in a little bit. So, but yeah, I use Linux, which can be a pain in the ass. OBS, I was having a hard time with it on Linux. But I don't know. Maybe I need to somehow make my streaming PC Linux. Because development is a lot easier. So like, yeah, I only use one GPU on my work PC. Like I went to my streaming PC here. So this is you can see on you can't see it. Let me adjust my video. On the left, you can see like the taskbar, I guess. On the left, it's Ubuntu. I like to hide like this. There we go. But on here, my stream PC, you can see my Windows bar right here. Yeah. Oh my gosh. So like, okay. It's recording my mouse pointer to be like normal size. But I made it big because I thought like it'd be easier for everybody to see, but it's just coming up normal fucking size. What the fuck? At least it's pink. But yeah, this contains my OBS, and then I got like VTube Studio here, and then I got my Steam. Steam runs with that, and oh, my beacon though. I don't think there's any. That's a problem. I don't think there's any like Linux support for a beacon. That uses my this is my microphone and all that setup. Yeah. Ew. But Windows, like OBS is more stable on Windows. And when you're streaming, you need stability. Like big time. Let's close it. Now this records it big. Like I made my mouse huge. Work by being trained. Did I read this shit already? Since it's become a default architecture solving all AI tasks. Some tasks lend themselves to transformer encoding structure, while others are better suited for decode. Still, the other tasks are used for encoder decoders. Language models work by being trained to predict the probability of a word given the context of surrounding words. This gives them a foundational understanding of language that can generalize to other tasks. There are two main approaches for training and now I understand the padding. There are two main approaches for training a transformer model. Masked languages, MLM, used by encoder models like BERT. This approach randomly masks some tokens in the input and trains the models to predict the original tokens based on the surrounding context. This allows the model to learn bidirectional context, looking at words both before and after masked word. Hopefully somebody out there already made like a package for that, because I don't want to have to write something like that at all. Yeah. Causal language model, CLM, used by the decoder models like GPT. This approach predicts the next token based on all the previous tokens in the. It shouldn't be like too hard, but I thought this would be like, hey, let's build a model, and this course here, and then we just build a model. But it's not been the way. The model can only use the context from the left previous tokens to predict the next token. Yeah. Yeah. Okay. In the transformer library, language models generally fall into three architectural categories: encoder models only, like BERT; decoder models only, like Ernie. These models are a bidirectional approach to understanding context from both directions. It's like, never mind. They're best suited for tasks that require deep understanding of text, such as classification, name entity recognition, and question answering. You know, like, I'm glad I'm like going through this, because like I kind of like, I didn't know like what models do this, and like I thought almost all models use both encoder and decoder together, and I didn't know there was just a decoder. So I am kind of glad I am like going over this, and you know, and not skipping too far ahead and everything. I am learning, and I am going to be forgetting it soon. These models process text from left to right and are particularly good at text generation tasks. They can complete sentences, write essays, or even generate code based on a prompt. Encoder, decoder models such as the T1000 and BERT. These models combine both approaches, using an encoder to understand the input and a decoder to generate output. Ooh, that's what I want. They excel at sequence-to-sequence tasks like translation, summarization, and question answering. So, okay, maybe you like want to have a couple like encoders for like maybe like image and the words, and then and then you feed like the stuff into. Can you feed the stuff? Oh, you can feed the stuff into the multi-head. You can feed the encoder into here. The multi-head attention. All right. As we covered in the previous section, language models are typically pre-trained on large amounts of text data in a self-supervised manner without human annotations, then fine-tuned on specific tasks. This approach, known as transfer learning, allows these models to adapt to many different NLP tasks with relatively small amounts of task-specific data. In the following sections, we'll explore specific model architectures and how they're applied to various tasks across speech, vision, and text domains. Yeah, I think like I'd want to have the AI also like look at whatever I'm looking at. That's for sure. Yeah. Like if I'm playing a game, I would want it to know like what I'm looking at. I don't know. Like comment on it. Understanding which part of the transformer architecture, encoder, decoder, or both, is best suited for particular NLP tasks is key to choosing the right model. Generally, tasks require bi-directional context use encoders. Task generating text use decoders, and task converting one sequence to another use encoder decoders. What? Well, text generation. Text generation involves create a coherent and contextual relevant text based on a prompt or input. GPT-2 is a decoder-only model pre-trained on a large amount of text. It can generate convincing, though not always true. Bullshit, it spoke the truth. Text given a prompt that can complete other NLP tasks, like question answering, despite not being explicitly trained to. Text imposition embed. Are they going to talk about this? Oh, maybe they are. I'm going to grab a drink real quick. I got one in the other room, so I'm going to just grab it. I'll be right back. I think it also helps that I'm like reading it out loud too at the same time. So it's like, it's reinforcement learning. Ha! Okay, my glasses are dirty. So the bad thing about glasses is that my model doesn't blink as much as I do in normal life. Ha! See, now I'm blinking. And now with my glasses on, I'm blinking. It does like a little bit. But the glare on my glasses will kind of like fuck it up. All right. Classification? What? For yeah. Well, the paper that started all this was Attention is All You Need. And that was published in 2017, I think. And they were saying, they had like a timeline. Oh gosh, let me duplicate this. What is this? All right, here. I am going to set up introduction. What if I just go to LLM course? Let's see what this does. Okay. I think I want to do this. I didn't even see this. What the fuck is this? This is important. I didn't even see the setup part. All right. Let me do this. Studio Live. I am going to. Should I put it in my. I'm going to put it in the description. So I'm going to put it here. This is my Ultra Derek account. Course link. There we go. Save. Let's go to my other channel. Switch accounts. I skipped the like setup part. I didn't even know the setup part. I did chapter 1. So I'll have to like go to that part when I need to. Because we haven't been building one at all yet. Okay. I've already. Course link. So if you want to go back and look at it, I think they have a timeline on one of them that answers like when chat like GPT-2 was released and all that shit. I guess I can like maybe I can use my Twitch one here. We don't really have descriptions for this, but create dashboard, creator dashboard. Course link. There we go. Something went wrong. What? Fuck you, Twitch. Can I pin it here? There we go. We'll do it until end of stream. There we go. All right, we did it. Okay. Is it pinned? Yeah, it is. All right. My pleasure. I'm going to just delete this here because we don't need it. So yeah, I guess I'll go back to that. Welcome to the HuggingFace course. This introduction will guide you. If you're just starting the course, we recommend you take a look at chapter 1, then come back and set up your environment. Okay. Try to code yourself. All the libraries that we'll be using in this course are available as Python packages. So here we'll show you how to set up the Python environment. All right. Of course, this relies on having a HuggingFace account, blah, 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 blah. Pip install transformers, import transformers. Ew. Using a Python virtual environment. Vim. All right. So I kind of got that all set up. I got like a GPU server here. So I kind of got most of that set up. I don't have like a Python environment. And I'm not like a Vim user. Like I'll be using, when I do the coding, I will be using my VS Code. Plus VS Code, like they have like they have like, this is installed. How much of this shit do I have? Remote Explorer, so remote development. Yeah. So I'll be doing something like that. I'll be using the remote development, which I need to like connect to a host. What is this tunnel to host? I don't know. So add a new SSH host. SSH Ubuntu at 192.168.55.50. There we go. Yeah, there. Connect. So it's logging into my host. I'm logging into the PC there. I think VS Code is open source, but it's Microsoft, so we got that going for us. So yeah, this is, I can like open a folder. So it's not going to come up as normal. So I do have a programs folder. I've already set up like Comfy UI in it. Like, so like I go to CD programs and then LS, I got Comfy UI there. So yeah. But now I'm like, I can now develop on this server, on this host. Yeah, it's matured a lot since when I first started using it. It's matured a lot. Not gonna lie. All right, so GPT-2 uses byte pair encoding (BPE) to tokenize. I don't like the word token. I don't know why. It makes it seem like it's not as serious. To tokenize words and generate a token embedding, positional encodings are added to the token embeddings. I think like token, like we got our token black character and our token Asian character and our token white character. That's what I kind of think each time I see the token black guy. So like, oh man, one of the best movies is like Not Another Teen Movie. Fucking hilarious. And this one black guy will like introduce himself as like, I'm the token black guy. You can thank Pippa for that. Fellow Kapipi. That's cool. Yeah, a lot of people don't see my like well, I guess I did like a collab with my Ultra Derek channel and my Nyana Neko channel. So that's kind of funny. I'm glad you're a fellow Kapipi, our dear leader. Quite fitting since she's playing like a lamb cult game right now in her chibi form. The input embeddings are passed through multiple decoder blocks. Okay, wait a second. Positional encodings are added to the token embeddings to indicate the position of each token in the sequence. Ooh. Cutest cult leader. Hell yeah, dude. Input embeddings are passed through multiple decoder blocks to output some final hidden state. Now this positional thing, I'm kind of interested in. I'm not like really sure what that does. But it looks like it's probably like its own vector. And maybe like the last, I don't know, 4 things would be like the last 4 bytes or whatever would be like or I say bytes, but it could be like, it could be a float or integer or whatever. I guess that can be in there. I don't know, like, do you feed it bytes or integers? Anyways, I guess like I would use like a typical like convolutional neural network. Like, I mean, you use like floating points, so 32-bit floats. I'm sure now they're like down to like 16 or 8 or whatever. I don't know what training though. Input embeddings are passed through multiple decoder blocks to output some final state. Okay. Within each decoder block, GPT-2 uses a mask self-attention layer, which means GPT-2 can't attend to future tokens. It is only allowed to attend to tokens on the left, not tokens to your right. Stuck in the middle with you. All right, different from the BERT mask token because it is mask self-attention. Holy shit, what the fuck? What are all these fucking what is that? The jargon, all this jargon shit. Okay. This is different from the BERT mask token because it is masked self-attention, and attention mask is used to set the score to 0 for future tokens. Like Andrew NG, he's like a professor that's like one of the leading professors on these things, and like I think it was YOLO. Yeah, probably shows you how to make the masks. The mask. He was like Andrew NG YOLO. Okay, is this him? Yeah, this must be him.
You've already seen most of the components of object detection. In this video, let's put all the components together to form the YOLO object detection algorithm. First, let's see how you construct your training set. Suppose you're trying to train an algorithm to detect 3 objects, pedestrians, cars, and motorcycles, and you won't need to explicitly have the 4th background class. So just 3 class.
I don't know if like, I thought he was going to talk about the paper.
Labels here. If you're using 2 anchor boxes,
but he said like this is like the hardest paper he's ever read, and he had to like reread it like several times.
The outputs y will be 3 by 3 because you're using 3 by 3 grid cell. By 2, this is the number of anchors. By 8, that's the dimension of this. 8 is actually 5, which is and then plus the number of classes. So 5 because you have PC and then the bounding boxes, that's 5, and then C1, C2, C3, that dimension is equal to the number of classes. And you can either view this as 3
I'm
by 3
pretty
by 3
sure
by
it
8
was this
or
video.
3 by 3 by 16. So to construct the training set, you go through each of these 9 grid cells and form the appropriate target. C for the first, all of the Y is anchor box 1. So notice then that
maybe he says it at the end.
Test set image is just noise. That. So
maybe
for
just
the
goes over
predictions. And so the effective object detection algorithms that also encompasses many of the best ideas across the entire computer vision literature that relate to object detection. And you get a chance to practice implementing many components of this yourself in this week's programming exercise. So I hope you enjoy this week's.
I think it was this one, but he was just saying like YOLO was like the hardest paper. I don't think it was attention is all you need. I think it was a YOLO one. Yeah. One of them was like, I had to reread this like over and over again. I couldn't really understand what they were fucking saying. I kind of feel like I kind of gotta, because I think it might be like just jargon. There's just so much jargon that gets like put into it and your brain's not used to it. And so you just got to reread it and reread it and reread it until the jargon just kind of like, you know, gets cemented into your brain. Also, it doesn't help that like a lot of these papers are ESL. And like, yeah. And like, it's all Greek to me, Neko. Yeah. It's all ESL. And like, on top of that, like, their professor might be ESL too. So like, a lot of these papers are written by like undergrad, or not undergrads, but graduate students. And then they'll have like their thesis professor help them with that, but they're also ESL. Yeah, I think that's part of the problem. Yeah, the output from these decoders pass the language model head, which performs as a linear transformation to convert the hidden states to logits. That's like a brand new fucking term. Leo AI tools. Summarize, explain. Okay, I understand. This is my first time ever using this. I don't need a fucking 20-page like essay on what logics are. Return from the raw unnormalized scores from the machine learning model. Okay. Outputs before they are converted into probabilities. Oh, okay. Oh. I just think they're just like, they're just a number. So like, if an AI is trying to classify an image, so like it would output like, if you had like a class, I guess, for these, and on the output, a lot of times like you'll normalize the output or something like that, or you might like, yeah, usually you'll like compress it to like 1 or 0, you know, like between 0 and 1. But this is like not that. So I guess negative would be like 0 or whatever. So it'd take these, it would like basically raise the bottom one up to 0, then like, yeah. It would just normalize this shit. Yeah. Hidden states into logits. The label is the next token in the sequence, which are created by shifting the logits to the right by 1. What? The cross entropy loss is calculated between the shifted logits and the labels to the output, the next most likely token. So, like, my graduate degree was on this, but it's been like 5 years since I've really like looked at a paper or whatnot, and I think this cross entropy is like the output. Basically, it's like grading it. So, entropy loss. Let's like double check this here. It's a loss function. Cross entropy loss is a fundamental loss function. So it's a loss function in the machine learning used by, yeah. So it takes like what the answers, what it answered and what the true answer is, and like does like a minus. So yeah, this is the loss function right here. Yeah. You did a degree on LLMs. I got my graduate. I mean, like, it doesn't say like you got a degree in AI. I got a master's of science in electrical and computer engineering, and but I guess I would say like my study was like AI, and yeah, I don't want to go into too much detail because it would totally. It could possibly like, because I have a published paper. And it could dox me. I should, yeah. It could, I mean, it's not like that, like popular, but like, it's pretty unique though. So if you, yeah, I went to see like how easy it is. Like if I talk about some of the things that I used in it or what it's about, like it'll definitely dox me, which, yeah. Performs a linear transformation. And like I didn't use Python either. So I guess I just hate Python too. I wish like these libraries are not done in Python. Like we really did ourselves a disservice by using Python on all this shit. And there's like a lot of work trying to make inference into a different language. Python, well, first of all, Python, I think it's single threaded. They might have just fixed that though. So everything runs on one single thread. Everything in the Python, like all the AI libraries are basically written like C++ and then moved to Python. So they're like hidden under a layer of C, like the C++ is hidden by a layer of Python in it. And I think Python's like really hard to read. Like I don't care what people say. Like I think it's fucking hard to read. Like it's hard to read to tell when something's like a matrix. Like you can do like something like I don't know. We'll just do like a new file here. Text file. You can have like let's say like a type matrix X. Now I don't really know X and Y, let's say. And then you can do like X times y, and like they will be matrices, and it will, and like let's say we put it into z, and it'll do the matrix operation. With like a regular like language, you'd have to do like z equals like mat multiply, and like be like x comma y, and that would do that, right? So yeah, this would be like a regular like language would do it. So you'd have to have an actual function to do the thing out, but like in Python, it will know like, hey, this is like matrix multiplication. It's kind of like MATLAB in that respect. Like MATLAB will automatically know everything's a matrix in MATLAB. Everything's a matrix in that. So I guess it starts off that way, and maybe that's behavior in it already. But yeah. So like that's why I found it like really hard to read, and plus it's not like type strict. So yeah, and plus like it's, how do I put it too? It's not like it doesn't build binaries. So when you make a program, you basically make a script from it and it reads from the script. It doesn't make like a binary output for a program. So everything's a fucking script. I find that really annoying. Okay. No, it doesn't. No, it doesn't compile. It doesn't compile into a binary. And that's what kind of, and like, oh, and I hate the fact like on Linux, like they write, like there's stuff that OS uses in Python. And if you like introduce new packages, it's already on here. And if you introduce new packages, it can fuck everything up. So that's why you got to build virtual environments. And that made it like, kind of like, for me, like it made it really hard to get into it. Cause a lot of them are just like, a lot of like, hey, how do I set up, like, how do I use Python on Linux? And so, but then they would use like the already installed Python, and you can't just be like adding packages to it because it can fuck shit up on your OS. And, but they don't really tell you like how to easily make like an environment, a development environment for it. So that I've always kind of struggled to get into writing in Python, at least in Linux. It's probably easier to do like on Windows. The output from the decoder is passed to a language model head, which performs a linear transformation to convert the hidden states into logits. Did I already do this? The label is then the next token in the sequence, which is created to shift the logits to the right by 1. The cross-entropy loss is calculated between the shift logits and the labels to the outputs of the next most likely token. Okay, I wish they would have it like slides to show what it's doing. The label is okay. I don't remember much, but it wasn't terrible, the setup. Yeah. I think like Windows, like you can go into the Windows store and just pick Python, right? Now, like accessing like programs through pip on Windows, pain in the ass. Like you can do that easy on Linux. You can use like pipx, right? Pipx, do we have that? Okay, so sudo apt install pipx. Pipx is like its own built-in environment, and like you can install packages or programs or whatever, like through the pip store on there, and then use it through this. But like I tried doing like the pipx through I think I tried doing pipx on Windows. I had a set I had to fucking find where they put the programs, and then like do like a deep search, like and create an environmental variable. Yeah, I had to create like an environmental variable for it. I think that's the word I'm looking for. I don't know why it's doing this. Can I go into it here? All right, let's like ping Google. All right, it's going. Let's ping Google. All right, it's just stuck. There it goes. Page top. It's only using 3.15 gigs. All right. This is my server I have. Pre-training objectives is based on causal language modeling, predicting the next word in sequence. This makes GPT-2 especially good at tasks that involve generating text. Ready to try your hand on text generation? Check out the Causal Language Model Guide. How to fine-tune, distill GPT-2 and use it for inference. I'm not mentally prepared for this right now. I am not mentally prepared for this. Okay. Yeah, I think this is like actually doing it. And it's getting so late right now. I don't want to like jump into it. Maybe it'll be something for tomorrow. So maybe I can start a new one of these. Let's create a new window. And I kind of want to close this. Let's close this. All right. And boom. I thought I grabbed you, bitch. I didn't need to create a new one. All right. So if they have like any of the new ones, I'll just kind of go to that and throw it in there. For more information about text generation, click text generation strategies, guys. Okay. Holy shit. This place is like teeming with tons of fucking data or information. Text classification involves assigning predefined categories to text documents such as sentiment analysis, topic classification, or spam detection. Ooh. I kind of need that with the data that I'm using. BERT is an encoder-only model and is first model to effectively implement deep bidirectional to learn richer representations of the text by attending to words on both sides. BERT uses word piece tokenization to generate a token embedding of the text to tell the difference between a single sentence and a pair of sentences. A special SEP token is added to differentiate them. A special CLS token is added to the beginning of every sequence of the text. The final output with the CLS token is used as the input to the classification head or for the classification test. BERT also added segment embedding to denote whether a token belongs to the first or second sentence in a pair of sentences. Huh. BERT is pre-trained with the objective masked language modeling and next sentence prediction. In masked language modeling, some of the percentage of the input tokens are randomly masked, and the model needs to predict these. This solves the issue of bidirectionality, where the model could cheat and see all the words and predict the next word. The final hidden states of the predicted masked tokens are passed to a feed-forward network with a softmax over the vocabulary to predict the masked word. Interesting. The second pre-trained object is next sentence prediction. The model must predict whether the sentence B follows sentence A. Half of the time, sentence B is the next sentence, and the other half of the time, sentence B is a random sentence. There, the prediction whether it is the next sentence or not is passed to a feed-forward network with a softmax over the two classes, is next and not next. All right, that's simple 1 or 0. Need a shower and go to bed. I understand. All right, have a good night. Thanks for talking. The input embeddings are passed through multiple encoder layers to output some final hidden states. Whoa. To use the pre-trained model for text classification, add a sequence classification head on top of the BERT model. The sequence classification head is a linear layer that accepts the final hidden states and performs a linear transformation to convert them into logits. The cross-entropy loss is calculated between the logits and target to find the most likely label. All right. So they're not doing like a not like softmax. I'm what's the thing? All right, I took a picture of it. I think I did. Oh yeah. Like a normalization layer. Yeah, they have a linear. Yeah. This is interesting because are these just like adding here? Like it takes this. So this is usually like a normalization. And then it goes here, and then it has like a linear layer. And use a softmax on that. What do they call those, like those layers that are neural network layers? Hidden layers. Okay, so let's go here. So this like incorporates other layers in it too. So I guess like nonlinear layer. I'm trying to think of that. So like you'll have like a linear and then a nonlinear. So it's interesting that they like output the nonlinear, the linear layer, which I had like best results with that, outputting the linear layer and then instead of like outputting a nonlinear layer. I did like whenever I like was writing mine, when I wrote my own or whatnot. So, but I've read places where they would use like a nonlinear layer as an output. So it's hidden in these neurons because in the neuron they will have like the linear input and then like and then run like an output like was it anything less than 0 is 0 and everything else is just the output. What do they call that? Like what was that called? Non-linear layer NNN. I guess CNN. Let's do CNN. Today on CNN. Applies to the activation function. So ReLU is the one that's like what I just said. So yeah. So they'll those neurons that they're showing, they have like the non-linearity already built into it. hidden states and forms a linear transformation to convert them into logits. This cross entropy loss is calculated. Okay, try your hand at text classification. Check out the complete text classification guide and fine-tune Distilbert and use it for inference. Inference. What'd I do? Token classification. Token classification involves assigning a label to each token and a sequence, such as in named entity recognition or a part of speech tagging. To use BERT for token classification tasks like named entity recognition or NER, add a token classification head on top of the base BERT model. Okay. The token classification head is a linear layer that accepts the final hidden states and performs a linear transformation to convert them into logits. The cross entropy loss is calculated between the logits and each token to find the most likely label. So they probably use like softmax or something. I don't know. Who fucking knows? Ready to try your hand in token classification? Try out our complete token classification guide. Oh my gosh. I am doing like get in there, bitch. Why is that not going in there? Oh, this. There we go. I am doing breadth search first instead of depth first search, right? Right? Question answering. Question answering involves finding the answers to a question within a given context or passage. Ooh, to use BERT for question answering, add a span classification head on top of the base BERT model. This linear layer accepts the final hidden states and performs a linear transformation to compute the span, start, and end logics corresponding to the answer. The cross entropy loss is calculated between the logits and the label positions to find the most likely span text corresponding to the answer. Ready to try your hand in question answering? So what I think I'm going to do is summarization. Let's read this. Summarization involves, let's do this. Question answering guide. I just want to have it respond to me. Fuck. There we go. What the fuck is this? It's a summarization, but it keeps on going. Usually you're supposed to stop at the one sentence. Wait a second. Oh, this is a type of like AI. Summarization involves condensing a longer text into a shorter version while preserving its key information, rename, and meaning. Encoder-decoder models like BART and T5 are designed for the sequence-to-sequence pattern of a summarization task. We'll explain how BART works in this section, and then you can try fine-tuning T5 at the end. I might do some of these, but I think I'm gonna like grab a model and then like work from there. That's like the best way to kind of like get into it. I'm thinking I'm kind of getting like the general idea for a lot of these. But like, I don't know, like maybe this, like the stuff for using transformers, like how to feed the data in, I think would be good. Because I can get kind of confused on that. Yeah. Parts encoder architecture is very similar to BERT and accepts a token and positional embedding of the text. BART is pre-trained by corrupting the input and then restructuring it with the decoder. Unlike other encoders with specific corruption strategies, BART can apply any type of corruption. The text infilling corruption strategy works the best through though. I mean, works the best though. In text infilling, a number of text spans are replaced with a single mask token. This is important because the model has to predict the mask tokens, and it teaches the model to predict the number of missing tokens. The input embeddings and the masked spans are passed through the encoder to output some final hidden states. But unlike Bart doesn't add a final feed forward network at the end of the predicted word. And to predict a word. The encoder's output is passed to the decoder, which must predict the masked tokens and any uncorrupt tokens from the encoder's output. Aha! This gives additional context to help the decoder restore the original text. The output from these decoders is passed to a language model head, which performs a linear transformation to convert hidden states into logits. The cross entropy loss is calculated between the logits and the label, which is the token shifted to the right. So this is like how they train them, right? Yeah, this is how they train them to be like usable. They had to do all these fancy smancy things to get these usable. So we're gonna grab this. There we go. We didn't print that there, did we? So I think like tomorrow, I'm going to finish reading this today, but tomorrow for the stream, my daughter is on, she doesn't have school tomorrow. Yeah. So I think, I guess I could have just asked chat in here. All right. Cause this would be like better than using the Leo AI. Let me close that. Yeah, so I'll be streaming tonight also. It's 1 a.m. for me right now. Translation. Translation involves converting text from one language to another while preserving its meaning. Translation is another example of sequence-to-sequence tasks, which means you can use an encode-decode model like BART or T5 to do it. The kind of like thing that I want to have is fucking simple. That's what I want to do. So BART adapts to translate by adding a separate randomly initialized encoder to map source language to an input that can be decoded into the target language. This encoder embeds all the past embeddings are passed to the pre-trained encoder instead of the original word embeddings. The source encoder is trained by updating the source encoder is trained by updating the source encoder positional embeddings and the input embeddings with the cross entropy loss from the model output. All right. So you just back propagate it. Like they don't really need to go like, wait a second. The source encoder is trained by updating the source encoder positioning embeddings and input embeddings with cross entropy loss from the output model output. That'd be interesting to see the function on that. Yeah. I'd have to see the function, see how it does that. The model parameters are frozen in the first step because like this here, like I see the words, right? But I don't see it in action, and seeing the code would really help. Let's see if they actually have the code in there. Pipeline. Wow. That's the config. Can we get like the actual fucking code? BART. This is interesting. The BART transformer. Auto model. What is this? Pipeline, auto model, transformer, CLI. Facebook BART large. So this is like, surface level shit. Okay. I guess like, is there like a GitHub page for us? Auto model. It said Facebook, right? So Facebook Bart large. All right. Bart AI model. Even like looking at a paper, like, code. I wonder if they like, is it open source? Okay. There it is. They have a LinkedIn thing. Interesting. So Bart. Oh no. Okay. I thought like the Bart would be in here. Examples. Where was that at? Yeah, these are just like readmes and shit. Summarize. Generate. Main. Okay. Oh my gosh. So this isn't the actual code. All right. Anyways. Fuck you. Did we read this? I don't really care about it. Cross entropy once following the multilingual version. MBART intended for translation and pre-trained on many different languages. Ready to try a hand in translation? No, not really. Modalities beyond text. Transformers are not limited to text. They can also be applied to other modalities like speech and audio, images, video, course, blah, blah, blah. Speech and audio. Did I have Bart here? Did they have like... I thought they had maybe... Oh. Let's go back. Yeah. All right, so... View PDF. Blah, blah, blah. Sometimes they'll like put the code in here. Like, how do they back propagate? How did you back propagate? The encoder. They didn't really go over it. The model, architecture, pre-trained BART, text infilling, fine-tuning BART, comparing pre-trained objectives, sequences. Yeah. These numbers. Token mask is crucial. Discriminate. Related work. Blah, blah, blah. Bye-bye. Let's start speech and audio. Let's start by exploring how transformer models handle speech and audio data, which presents unique challenges compared to text or images. Yeah, because like, yeah. Whisper is an encoding decoder sequence transformer pre-trained on 6 680,000 hours of labeled audio data. This amount of pre-training data enables zero-shot performance on audio tasks in English and many other languages. The decoder allows Whisper to map the encoder's learned speech representations to a useful output such as text without additional fine-tuning. Whisper just works out of the box. It does. It's fucking fabulous. Diagram is from Whisper Paper. So the Whisper Paper. Blah, blah, blah. It's nice. It's open source too. An encoder process that it's like the only like good thing that's come out of OpenAI. It's the only open source project that's out of OpenAI. They need to rename their company. It's such a fucking scam, dude. Okay, so I kind of like since I've been like reading this thing here now, like before when I looked at this, I did not really understand what they were going on at with this, but now I know like this is encoder blocks. So the encoder decoder, you got your encoder here and your decoder. Yeah. They don't show like how you back propagate, which would be nice. So I guess these are like things you get. Okay. So a log mail spectrogram. So the audio comes in under this, gets pushed in there, push it in, baby. And looks like it's a convolution 1D and a GALU. I don't know what a GALU is. 2 times that. What? Not sure what this means. Sinusoidal position encoding, transformer encoding blocks. Yeah. Self-attention, MLP. I had to like relook at what the MLP is. Cross attention. So this is the decoder and tokens in multitask training format. Maybe this is like the quick brown fox jumps over. Oh, so these are like flags or something? Maybe. So this is the input, then you have flags for the output. And how did it know like, how does it know this? Wait a second. Oh, wait, is it? Maybe it's like, interesting. Learn positional encoding. So this plus this. Not 100% sure what it's doing, but maybe that's the magic. Like it starts off putting the, and then it like cycles through the quick brown, right? So it's like, it's loading in these things. Yeah. Where did the SOT go in? Where's the SOT? What does SOT mean? I don't remember. Anyways. Encoder process input audio. The raw audio is first converted into a log mail spectrogram. This spectrogram is then passed through a transformer encoding network. I wonder if they like have like certain frequencies. They just kind of cap it off because like, fuck, dude, like, do you really need like a really super high frequency that normal people can't even really hear? Anyways, it'll be like kind of a compression. A decoder takes an encoded audio representation and auto-regressively predicts the corresponding text token. It's a standard transformation decoder trained to predict the next token given the previous token of the encoder output. Special tokens are used to the beginning of the decoder input and to steer the model towards specific tasks like transcription, translation, or language identification. That's cool. Yeah, because like you might have like different languages in there too. Like example, Henya the Genius. She speaks Japanese and English in there. Yeah. Whisper was pre-trained on a massive and diverse data set of, we know this, labeled audio data collected from the web. This large-scale, weekly supervised pre-training is the key to its strong zero-shot performance across many languages and tasks. Now that Whisper is pre-trained, you can use it directly for zero-shot inference or fine-tune it to your data for improved performance on specific texts like automatic speech recognition or speech translation. You know, that sounds like fucking good. Like, yeah, I kind of want to like go in there and yeah, I've just been using like the base thing, but maybe I can go in there and kind of make it a little bit more towards like what I want to use with it. And like, it's okay. So I think it came out in 2022 and they're still like updating it. Like they came up with the turbo model, which like works just as good as their large model. And it's a lot smaller. So you can use it on smaller GPUs. So OpenAI Whisper. So it's not like they just popped it out there and then stopped doing things with it. So yeah, this is it here. I don't know, this multitask training format. Okay. What's EOT? I'd have to like read this. Previous text token. Oh. What? They make it look like this here, like. Oh my gosh. I am very confused. Did I say? Like, I kind of understand this a little bit, but I don't really know what's going on here. Previous text token. Text tokens. Text only transcription allows data set specific fine tuning. Okay, setup, blah, 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 blah. So they got the turbo one. The large model, it's almost like half the size of the large model. It's about 6 gigabytes. The 10 terabyte or 10 gigabyte one. So now like you can use like a GTX like 1070. Let's say like you don't have relative speed 8x. So the large model is 1x. So it's like 8 times faster than the large model. Yeah. I wonder how they got it like faster. Like it's faster than the medium level size one. Like, how do they make it faster? Maybe it's like a completely different. Oh, it's a model. I wonder what kind of voodoo they did there. Whisper. Assets. So decoding timing. So like you can go into like the model PY. Yeah, so you can actually see the code for this one. Audio encoder, text decoder, Whisper modules. Is there a main? I think like you'd have to go to the. Is this the main? Did I go to the main? No. So what is this main PY? Okay. See, I don't know. Like, where's main? Assets. GPT-2 token. Oh my gosh. So this is the tokens. This, I might steal this. Look at this token. Who uses like IF, G, G? Is this like for like websites and shit? This is out of control. IQ0, IG1, IW. And so they'll use token. It's kind of like a compression. So that it's, yeah. Interesting. Mel filters. All right. I was hoping to go into like Whisper. Whisper. I was hoping to see the main. Where's main? Where is the main? Data. Notebooks? What's this notebooks? Tests. GitHub. Data. What's this data? This selection supplements the paper with more details on how we prepared the data for evaluation to help replicate our experiments. Oh, okay. Man, they did like a really good job. It seems like on this. This is the first time I've really like dug in deepish. Manifest readme approach PNG. I thought like it would be in here. Tests. No. Maybe it's in Whisper. I thought like the Python. I've only ever like, I never like installed this. I've always used pip. I've never installed the it raw. So yeah, I'm gonna have to use it. This will be like part of my thing. Pip install Whisper. A lot of times with these programs, like they'll open it up, and then like once the Whisper's done, it's not gonna keep it in memory. It's gonna close it, and then like everything's out of memory. So you, in order to like have something like another AI model, like you gotta, like if you wanted to run like concurrent to whatever you're making, you'll have to have this set up. You'll have to actually write something. I thought, where's the main? Oh well, we'll just go back. So last time they updated was, looks like 7 months ago. Yeah. So it's not dead. It's not dead at all. I'll start it. Oh, Billy. Automatic speech recognition. To use pre-trained model for automatic speech recognition, you leverage its full encoder-decoder structure. The encoder processes the audio input, and the decoder auto-regressively generates the transcript token by token. When fine-tuning the model is typically trained using a standard sequence-to-sequence loss. All right, that's understandable. To predict the correct text tokens based on the audio input. So there's a lot of training. Supervised training. Yeah, which makes sense. For something like this, you need supervised training. You can try our hand in speech recognition. Check out our complete automatic speech recognition guide. Yeah, we will do that. Man, plethora of information. Let me tell you. Computer vision. Now let's move to computer vision tasks, which deal with understanding and interpreting visual information from images or videos. Now, I don't know. There are ways to approach computer vision tasks. Split an image into sequence patches and then process them in parallel with a transformer. Then use a modern CNN like ConvNext, which relies on convolutional layers but adopts modern network designs. The third approach mixes transformers and convolutions. For example, convolutional vision transformer or VEVIT. We won't discuss these because they just combine the two approaches we examine here. VIT and ConvNext are commonly used for image classification, but for other vision tasks like object detection, segmentation, and depth of estimation. We'll look into DETR, Mask 2 Transformer, and GLPN, respectively. These models are better suited for those tasks. Image classification. The image classification is one of the fundamental computer vision tasks that let's see how different models architectures approach this problem. VIT and context use both. Image classification, the main difference is that VIT uses an attention mechanism while context uses convolution. VIT replaces convolutions entirely with a pure transformer architecture. If you're familiar with the original transformer, then you're already most of the way towards understanding VIT. Yeah, baby. Class bird call car, MLP head, linear projection of flattened patches. What the fuck? What are these? Patch and position embedding. What are the? Okay. So it cut it up in pieces. Boop, 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 and then put it in here like that. I'm surprised there's no overlap. Interesting. Interesting. Maybe you don't need it. Or maybe they do have it. Maybe there's an option to do overlap. The image is split into square into square non-overlapping patches, each of which gets turned into a vector or patch embeddings. The patch embeddings are generated from a convolutional 2D layer, which creates the proper input dimensions, which for base transformer is 768 values. The 768 comes up a lot. If you had a 224 by 224 pixel image, you could split it into 196 16x16 image patches. What? 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 Is this okay? I think I know what they're getting to because there's color like pixels, right? So let's just double make sure. So 196, 16 times 16 is I was doing this with my left hand, so times 16, and I don't have a numpad. Like 256. Ooh. And then times 196. Okay, so that's 5. Okay, it's 50,176. I think all right, let's copy this. Actually, it's up there, right? So 224 times 224. Okay. All right. This really threw me off. But it makes sense now. Okay. Just how the text is tokenized into words, an image tokenized into a sequence of patches. That's interesting. A learnable embedding, a special CLS token is added to the beginning of the patch embeddings, just like BERT. The final hidden state of the CLS token is used as the input to the attached classification network. Other outputs are ignored. This token helps the model learn how to encode a representation of the image. The last thing to add to the patch and learnable embeddings are the position embeddings. Because the model doesn't know how the image patches are ordered, the position embeddings are also learnable and have the same size are learnable and have the same size as the patch embeddings. Finally, all the embeddings are passed to the transformer encoder. The output specifically, it's also gray. Like this would be gray. I'm sorry, I had to go back to it. So yeah, it's gray. Usually there's which was driving me off because it would be 224 by 224 by 3. That would be it. So maybe for this here, the 196 16 by 16. Let's say if you were to if it was a by 3 pixel image with color, then it'd be a 16 by 16 by 3 here at the end here. Anyways, the last thing, image patch learnable embeddings are the position embeddings because the model doesn't know how the image patches are ordered. The position embeddings are also learnable and have the same size as the patch embeddings. Finally, all the embeddings are passed to the transformer encoder. Last thing to add to the patch and learnable embeddings are the position embeddings, because the model doesn't know how the image patches are ordered. The position embeddings are also learnable, okay, and have the same size as the patch embeddings. Finally, all the embeddings are passed to the transformer encoder. The output, specifically only the output with the CLS token, is passed to a multi-layer perception head. MLP. VIT's pre-trained objective is simply classification. Multi-layer perception head. I'm not really sure what that is. Did you just fuck me up? Fuck you. Is it fucking doing this? All right, this is too much. I just need like ready to try your hand at image classification. Check out the image classification guide to learn how to fine-tune VIT and use it for inference. All right, text to speech. TTS. Hell yeah, brother. Man, I'm gonna become an expert at this shit. Tomorrow we are gonna go through, like, we're gonna play with the code. Like, we'll run with this, right? I think causal language, yeah, modeling. We'll play with these things and play around with it. And I guess I do want to like see like how they train and stuff like that, like how the code was written. That would really be helpful. Yeah, baby. So let's see who's available. Is Cleo still around?
Coder-decoder models like BART and T5.
Let's raid. Should we raid Mari? Let's raid Mari. Monday.
Fries is a bigger hit of the game.
All right.
But this looks better for your dollar.
Who
wants a plastic souvenir bowl? One thing I'll never understand is the souvenir popcorn things they make for movies.
I totally get it.
And it's like Darth Vader's whole body, and the top of his head is cut out, and that's where you put the popcorn.
Put his mouth.
And there's like a tiny hole that you put your hand in to get the popcorn out.
Yeah, that's what the hole's for. Yeah. Duh. Anyways, hey guys, I appreciate it. People on my Nyata Neko channel, I'm sorry, I can't rate anybody on my Nyata Neko channel. I don't have enough. I need 1,000 subscribers. So like, comment, subscribe on my stream. Eventually y'all can get. Eventually I want to move stuff like this to my Nyata Neko channel. So I kind of do everything with it. I don't want to, like, my Ultra Derek channel, I don't want to really have like this kind of stuff with it. So but anyways, yeah, I appreciate y'all, and yeah, I will catch you all on the flip side. Stay out of trouble. Stay classy. San Diego.
I got lucky.
Bye-bye!
Stop showing me this